let us consider a very special space called as the signal space, which we will be encountering quite often in our study. This signal space is actually formed by signals. Okay. Let us consider two signals S1 of t and S2 of t, maybe they are of this particular shape. Okay. They are of duration t1 and t2, okay. That is one signal. Then I have one more signal here which goes on this particular case, say t2 and t3. So, I have to revise my statement. What I want to say is that each of these vectors are from duration t1 to t3. Okay. This vector is 0 from t2 to t3, whereas this vector is 0 from 0 to or t1 to t2. However, these are the two signals that I am considering, S1 of t and S2 of t. Okay. I might have used the same word as signal and a vector, but I hope by now that we have learned to recognize a signal as a vector. So, I will use these words interchangeably. So, hopefully there should not be much of a confusion. Okay. So, you consider two signals S1 of t and S2 of t of this particular fashion, and then I can add them to form these signals. Okay. So, I can add them to form this signal, I can also add them to form this signal, I can add them to form this signal. Okay. So, these are all different signals S3 of t, S4 of t and S5 of t, which I have obtained by simply adding S1 of t and S2 of t. In this case, you can see that S2 of t has been multiplied by some larger number and then added to S1 of t. Here you can see that S2 of t has been multiplied by -1 and added to S1 of t. Here you can see that S1 of t has been shrunk, whereas S2 of t has been expanded in the reverse direction, that is by multiplying it by minus of a large quantity, right. But in all these vectors, and there could of course be an infinite number of such vectors, right. If I call all of these possible combinations as a span S, right, this span or the subspace which is now spanned by S1 of t and S2 of t, right, which will be acting as though they are unit vectors or the basis vectors. They are not yet unit vectors, they are the basis vectors for us. So, as though S1 and S2 are the basis signals or basis vectors for us, if I take any linear combination of, there could be an infinite number of such linear combinations resulting in an infinite number of signals, but each of those signals can be built up just by stretching and expanding each of those S1 of t and S2 of t. Okay. We are not allowed to move it outside the domain, but we are allowed to multiply it by any real number. Okay. So, such space is called as the signal space. Signal space consists of all those S of t's, okay, or all those Sk of t's such that each Sk of t can be built up as linear combination of these two vectors or these two signals S1 of t and S2 of t. Okay. If you consider a source, a digital communication source, this source generates m possible waveforms. Okay. Each of those waveforms would be some binary symbol or it would be a data symbol associated with that. Each of the waveforms are nothing but signals as functions of time. Okay. Waveforms are functions of time or they are essentially signals. So, each of those m possible waveforms called as S1 of t to Sm of t, okay, we should be able to express each of those m possible waveforms as some linear combination. Okay. If I am looking at the ith waveform Si of t, where I is equal to 1, 2 up to m, if I can write this Si of t in terms of any ith signal as say Sij phi j of t, right, as a linear combination of n signals, n less than m, right, then this Si of t can be very uniquely specified by Sij components, right. Si of t can be specified by writing this as Si1, Si2 and so on up to Sin, the transpose just to show the column vector. So, this particular thing uniquely specifies the signal Si of t. Of course, you might want to ask what is this phi j of t? These phi j of t are called as basis functions and we should be able to find n such basis functions. That is, given a set of m signals, okay, we can find n which could be less than or equal to m. In the worst case, n will be equal to m. We should normally be able to find n such basis functions. Okay. Through these basis functions, I am able to expand or write down any or represent any m possible waveforms. Okay. So, these are the basis functions. These basis functions, let us call this as phi j of t. Okay. J is equal to 1 through n. Now, we will not go into the details of how to obtain the basis functions. Okay. I will simply assume that process is covered elsewhere. You can actually generate them by going through a process called as Gramschmidt Orthogonalization. Okay. So, in this procedure, or this procedure allows you to get n basis functions from a given m waveforms. Okay. If I have given you say 16 waveforms, I should be able to find n which is say maybe 2, 8, 10 depending on the waveforms that I have been given. I should be able to find n such basis functions. Okay. N such basis functions or n basis functions which can be represented as phi 1 of t to phi n of t. This would be an efficient representation if n is less than m. Okay. So, this word orthogonalization might tell you or might remind you of another word, orthogonal. You know, in fact, orthogonalization would be a process of orthogonalizing something, right. So, what is this orthogonal word? Well, we go back to the vectors, vector v and vector w. Okay. We call these two vectors as orthogonal to each other if their inner product is 0 or if their dot product is 0. So, this brings up an important notion which is geometric in notion called the dot product or the inner product, or sometimes called as the scalar product. We define this dot product or inner product or the scalar product as, or we denote it by v dot w. For a 3-dimensional Cartesian coordinate space, we are familiar with the physical interpretation of this, right. I take the vector w and then I have the vector v. The dot product basically gives me the length of v along w, right. So, this might be the definition that you might have seen. V dot w is actually length of v along the vector w. Of course, both v has to belong to the same vector space, w also has to belong to the same vector space. So, if they belong to the same vector space, then v dot w will give me the length of v along w, right. This is in physics textbooks or in electromagnetics textbooks, you would find this as v magnitude of v into magnitude of w cos of theta vw, where theta vw will be the angle between the vectors v and w. The geometric notion is that by performing the dot product, you are able to find out the component of v or the length of the component of v along w, but this is just the length. If I want to find out the vector component of v along w, then I have to take this dot product, which is this number, and then multiply with the unit vector along the w axis, right. So, I have to multiply this one by the unit vector. So, this orange color one is my unit vector along the w axis. Of course, this is symmetric geometrically, right. So, if v, the component of v along w is exactly equal to the component of w along v, right. So, that would essentially be the physical interpretation of this inner product. But as you might suspect, we might want to generalize, or we will be generalizing this notion of inner product. We will also write down the inner product with a different notation. We write down this as v w, we put a bar here. Okay. So, I define the inner product by certain rules. I first of all claim that this is the notation for the inner product. I claim that v upon v itself must be greater than or equal to 0. This is of course true unless v happens to be itself equal to 0. Unless I take 0, this is true. Geometrically, what does the inner product of a vector with itself give you? you go back to the Cartesian coordinate system Vx x hat plus Vy y hat, I will just restrict it to 2 dimensional, then the inner product of V with itself is given by Vx square plus Vy square, which is actually length of the vector V square, correct. This is giving me the length of the vector V square. In other words, if I want to find out the length of the vector V, I should take the inner product of V with itself and then take the square root of it, okay, and then take the square root of it, assuming that these vectors are all real vectors, okay. Now the other rule that we want to say is that if I take the vector V, or if I take the sum of two vectors, okay, call this the sum as V plus W, and then I take one more vector which is say Y, this should be equal to V y plus W y, okay. Another criteria for me would be, if I take the scaled vector and then take the inner product, this should be equal to magnitude of alpha times V W, right. The inner product of a scaled vector with the vector W will be magnitude of alpha times V W. This magnitude I am using because this alpha could be real or complex, okay. So this would be the notation. There are also couple of other points about the inner product, that if I take the vector V with the vector W and I say that vector V and vector W are complex vectors, that is they belong to complex vector space, then this should be equal to W and vector V complex conjugate. That is, if I interchange the order, then I should get the complex conjugate, provided this is for the complex vector space, okay. For a real vector space, that is a vector space that is consisting of only real vectors, real valued vectors, you can drop this conjugate, right. It would not matter because it would give rise to a scalar or a real number, and real numbers we do not have this conjugate property, okay. Now these are the rules by which we can construct the inner product, right. Now let us take an example of our signals and then see if we can define the inner product, right. So I take S of t one signal and say G of t as another signal, both belonging to a certain signal space S, okay, both belonging to a certain signal space S, and if I define the inner product as S of t into G complex conjugate of t, I can assume that these signals are complex valued signals. I am assuming them to be complex valued. For real valued signals, you simply have to drop this conjugate term, okay. So this would be S of t multiplied by G complex conjugate of t and then integrated over the duration, whatever the duration that you have considered originally for the two signals, you have to integrate them over the duration, right. And now let us see whether this particular definition, this would be the inner product of the vector S of t and G of t, this is the definition. If I define this way, will I be able to satisfy all the rules of inner product? Certainly yes. If I take interchange G of t and S of t order, in place of G of t getting complex conjugated, I will have S of t getting complex conjugated, which will satisfy this last criteria for me, right. If I multiply S of t by a number alpha, then alpha will go inside. If alpha happens to be a real number, then alpha will simply come and multiply S of t. So I can pull alpha out of the integral as long as it is constant. So the entire inner product is simply scaled up. The third, going in the reverse way, this one is if I consider the sum of two signals S of t plus G of t, and then I want to find out the inner product of this sum with another signal, say Y of t, it is very straightforward that this equation is also satisfied. One last thing would be, if I take S of t and then take the inner product of that with itself, this will be S of t magnitude square of dt, and if I consider this to be an infinite dimensional signal, that is it is going all the from minus infinity to plus infinity, then it is clear that this integral does not always exist, okay. If we demand that this integral must exist and must be finite, that is the reason why we had earlier also imposed this condition, okay. It is not necessary that this condition be imposed, okay, but this be imposed in this way. There are other ways of imposing similar conditions, but for us it works out very nicely, because we know that this integral of S of t magnitude square of dt will actually give me the energy of the signal S of t, right, and this signal is also the length square, right, length of S of t square in some sense. So, you can make a connection that length is equal to square root of energy, okay, and this length is called as norm in vector space theory or the signal space theory, okay, and this norm is denoted by writing two lines like this, okay, S of t, and therefore energy is basically norm square, okay, energy is norm square, norm itself being the length. I hope these connections are clear. What you have to remember is that we started off with signals of the form S of t and G of t of over a certain duration. This duration could be finite or this duration could be infinite, but all such signals were belonging to this space S, and then we have shown that if we define the inner product by this particular way, right, we will be able to talk about the inner products of S of t. In fact, in signal theory this particular integral has a name, this is called as correlation, right, this is the correlation of S of t with G of t. If they are perfectly correlated, like if they are the same, then you get to the energy of the signal. If they are completely uncorrelated, you get to the inner product will be equal to 0, or they are essentially uncorrelated, right. So, when they are uncorrelated, we call them as orthogonal signals. We sometimes denote this by writing this perpendicular and say S of t and G of t are orthogonal if their inner product vanishes, right. This is for the signal. If you go back to this Cartesian coordinate example, they will be V and W vectors will be orthogonal when they are perpendicular to each other, right. So, this perpendicularity is nothing but orthogonality. Now, why is this orthogonality important for me? Because if you go back to the Cartesian coordinate case of decomposing a vector into its components, you will immediately notice that the vector x is perpendicular to vector y, correct. So, this additional property that the basis vectors are mutually perpendicular. If you were to consider 3-dimensional case, then x is perpendicular to y, x is perpendicular to z, y is perpendicular to z, right. So, they are all mutually perpendicular to each other. Moreover, what is the length of vector x or the norm of the vector x is 1, correct. That is why these are called as unit vectors, vectors having magnitude 1, which can be stretched or shrunk to form additional components. So, what would be the norm of this Vx into x hat vector? What is the norm of this vector? Well, it is nothing but magnitude of Vx, because it has to be positive, right. So, this is the norm of this particular vector, okay. Remember, Vx is just a number, it could be positive, negative, it could be complex. When you multiply that one with x hat, assuming in the Cartesian coordinate system, then Vx can only be real, it could be positive or negative or could be 0, but when you take a number and multiply it to a vector, you get a vector, and norm is specified for vectors, not for scalars, okay. So, this is the notion of norm. Now, you go back to the signal space that we talked about, right. We had signals S1 of t through Sm of t, there were m signals, and we said that if we could find n basis functions, right, we could find n basis functions phi 1 of t to phi n of t with n being less than or equal to m, right, then I can expand any vector sk of t or any signal sk of t as the sum of these vectors, right, phi I of t. I can expand this as a combination of these basis functions phi I of t. Further, if I choose these basis functions in such a way that if I take two basis functions and find out what is their inner product and say that this inner product is equal to 1 in case the vectors happen to be the same, or it would be equal to 0 when these two vectors or these two signals or basis functions are different, then what I obtain is a set of orthonormal basis functions, okay. These are called as orthonormal basis functions. ortho because they are orthogonal to each other. So, this is the set I have orthogonal to each other. You can take any two signals, they will be mutually, the inner product will be 0, that is they will be completely uncorrelated, right. These are signals, therefore, they will be uncorrelated. However, if you consider the inner product of the signal with itself, you will end up having that inner product equal to 1, just as that would be the norm for a unit vector, right. So, that is why they are called as normalized, their lengths in some sense has been normalized. Okay. So, this forms the so called orthonormal basis. Now, we are ready to close our discussion on the signal space. What we have found is that any signal Sk of t, which is a time duration waveform, can be uniquely represented or specified by giving its components Ski, right. What are these Skis? Skis are obtained by taking the signal Sk of t and then forming the inner product of this with the ith basis function. Okay. So, this would be the Ski, and the set of Skis, how many Skis should I have for each Ski? This would be Sk1, Sk2 all the way up to Skn, right. So, if I arrange them in the form of a column vector, I can write down this in the shorthand notation and write this as Sk bar, which will now be a vector. Okay. So, Sk of t is a waveform or a signal which has now been represented as a vector. Okay. Can I talk about inner product of two vectors Sk of t and Sq of t? Yes, what would be this inner product? Go back to the definition, this would be Sk of t, assume that these are all reals. So, this would be Sk of t, Sq of t, the complex conjugate thing will go away, multiply by dt, right. This is the inner product definition over whatever the duration these two signals have been specified as, right. Now, in place of Sk of t, you can write down its representation in terms of Ski, right. This would be Ski phi I of t summation I equals 1 to n, and for Sq of t I can do the same thing. This would be Sqj phi j of t, where j is equal to 1 to n. There is an integral that is still going on, right. Now, I can interchange the order of summation and integration. Okay. So, I can write this as I and j, this is a double sum. I can write this as Ski Sqj, and I have the integral of phi I of t, phi j of t dt. But I know that these two, this is nothing but the inner product of phi I and phi j, which would be equal to delta ij, that is they would be equal to 1 when I equal to j and they would be 0 otherwise, allowing you to collapse this double sum into a single sum and you get Ski Sqi. This is nothing but taking the vector Sk, transposing it, multiplying it by Sq vector, okay, or component by component multiplication. This is the inner product. Okay. I will leave as an exercise to find out S3 of t and Sn of t, but I would like to very quickly give a geometric representation, right. Since I can write down S3 of t, for the signal space example that we considered, I can write down S3 of t as S1 of t and S2 of t. From this S1 of t and linear combination of S1 and S2, I will obtain a different combination. Let us call this as beta 1 and beta 2. In place of S1 I will get phi 1 of t, and in place of S2 I will say I will use phi 2 of t, where phi 1 and phi 2 are the orthonormal basis functions which have been obtained from S1 of t and S2 of t. If you go back to S1 and S2, they are already orthogonal, therefore their orthogonal functions would also be phi 1 of t and phi 2 of t, which have been scaled up to get the energy equal to 1. So, I can write down this S3 of t in terms of these vectors, or equivalently simply specify this in terms of beta 1 and beta 2, right. Then geometrically I can represent this as, this is phi 1 axis, phi 2 axis. I can represent this one as this vector whose components are beta 1 and beta 2. We will talk about it later. So, if we go back to the signal space, S3 of t can be written as some linear combination of S1 of t and S2 of t. If you recall what S1 of t and S2 of t looked like, this is how S1 of t looked and this is S2 of t looked, right. Over the duration t1 to t3, right. So, over the duration t1 to t3, these two functions are clearly, the inner product of these two are clearly is equal to 0, meaning that these two are orthogonal signals already. If you take this signal S1 of t and divide this one by its norm or the energy of this signal or square root of the energy, I will be able to obtain the corresponding orthogonal or orthonormal basis functions, right. So, how do I generate the basis functions? Take the signal and then scale it up such that its energy is equal to 1. So, I get two basis functions which I am using a caret to indicate there, there is a hat on top of it. Okay. These two are the basis functions, right. From these two basis functions, I can write down this vector, right. I can represent this signal S3 of t as say 1 unit of phi 1 of t plus 2 units of phi 2 of t, for example, right. I can write down S3 of t as 1 unit of phi 1 of t and phi 1 of t and 2 units of phi 2 hat of t, or equivalently I can simply give coordinates 1 and 2 to this, right. So, in the phi 1 and phi 2 plane, right, if you imagine this as phi 1 plane and phi 2 plane, we will drop the time notations because phi 1 of t itself can be written as 1 times phi 1 of t plus 0 times phi 2 of t, right. So, this can be written as, well, let us not go to this way, this is not the correct one to write. We can simply consider this phi 1 and phi 2 as vectors or as two mutually perpendicular vectors, right, and then any vector S3 of t can be written in terms of this 1 and by giving them the combinations alpha 1 and alpha 2, right. So, in this case what would be S1 of t? S1 of t itself will be phi 1 of t times S1 of t's norm, okay, and S2 of t will be plus 0 times phi 2 of t in this particular case for S1 of t, and it would be 0 times phi 1 of t for S2 of t plus S2 of t norm times phi 2 of t. So, this can also be equivalently represented by two numbers, which is S1 norm, which would be a number, right, and 0. This one can be written as 0 S2 of t norm, right. So, I can now represent all these three waveforms in terms of their corresponding vectors. So, this is S3 vector, this is S1 vector, this is S2 vector. So, S1 vector may be here, S2 vector is this one, okay, because this length would be the norm, or this length will give me S1 of t norm and this would be the length S2 of t norm, okay. Then S3 of t can be written as units of say 1 and 2. So, let us call this as 1 and this as 2. So, this would be the S3 vector, okay. So, this is S1 vector, this is S2 vector and this is S3 vector. Now, I can very clearly see that if I were to project or if I were to take the inner product of S3 with S1, I will get a certain number, right. So, it has component along phi 1 and component along phi 2, okay. I have used phi 1 and phi 2 here, but you could have used any other numbers, you could have called this as x, you could have called this as y. The basic idea is that every signal in that signal space, we should be able to write it as a linear combination of the basis functions. From the basis function that we have written, whatever the numbers that we are multiplying, those numbers you can collect to form a column vector and that would be represented on the corresponding plane, right. On this same representation, what can you say about the distance between two vectors, say S of t and g of t? What would be the distance between these two vectors? I know that S of t, if I expand it in terms of the orthonormal basis functions, can be equivalently represented as a vector S. This would be represented equivalently as a vector g, correct. The distance between these two vectors is nothing but S minus g norm, right. This is the distance or distance square, this is the distance between S vector and G vector square is nothing but this particular thing, right. So, on some space, in this case it was a 2-dimensional space, maybe in this particular waveform maybe it is a 3-dimensional space or maybe a 4-dimensional space. I will be able to write down S of t vector by giving its vector vector representation. I also have the vector G, and this would be the difference vector S minus G, and this distance or the difference between the two will be given by the length or the norm square of this particular vector. Okay. So, this is how we can write down or we can give a representation of vector to signal, right. So, we can think of a signal as a vector, right, and this decomposition of any of the source waveforms, say Si of t or Sk of t, does not matter. So, this decomposition of Si of t into the j unit or orthonormal vectors, orthonormal basis functions would give rise to representation of the waveform as a vector on the appropriate signal space or appropriate space that is spanned by the basis functions phi of t. Is that okay? So, this is phi j of t. So, the equivalent way in which I can write down this is by giving it as a vector and call this as vector Si. Okay. These concepts of the distance between two vectors and how to represent these or how to utilize these vectors, I mean signals as vectors, will be very important when we discuss digital modulation techniques, where we will see that ASK, BPSK, QPSK, QAM, all these waveforms can be thought of as vectors in a geometrical space. Even noise can be thought of as vector in that space, and then we will be developing lot of intuition about how to go about calculating the probability of error and every other, I mean all other different metrics that are involved with this. Okay. So, in the next module we will be utilizing these concepts. So, this module was largely a background material. From next module we will be utilizing these concepts to discuss the modulation methods. Thank you.